Okay, so I'm going to spend about 2 minutes going through this PowerPoint. The Softree Optimal demo will take 15 minutes if I talk really fast, and then we've got some time for questions. And I hope you guys still have 20 minutes open for us.
Yeah, we're good.
Okay, so what we've done here is, optimization is thrown around. The word is thrown around a lot. This is mathematical optimization. There is also human optimization, and I'll talk about that too. But the idea here is we've got some pretty heavy-duty math and also some very powerful software in the background that solves optimization problems, in particular mixed integer linear programming problems. Okay, it's used all over the place. Not very much in civil engineering, but it's certainly used for, you'll mostly come across optimization in things like scheduling, but it's used all over. Okay, so we've done vertical alignment optimization. We want to do horizontal alignment optimization. We are working on it. We're partnering with UBC here in British Columbia, and we're doing some preliminary work on horizontal, but currently we've only got the vertical end done, which means that you have to have a horizontal alignment first. Designing a road is an iterative process. Anyone who's done any engineering knows that it's more of a cycle than a linear procedure. So you're going to have to calculate a horizontal or design a horizontal alignment. You're going to have to design cross-sections and other things to do with your alignment, and you're going to then have to vertically align your road. And when you think you've got something that's good enough, you're finished. We can address the vertical alignment part. And what we can do is we can speed up that part a lot, so this cycle can go faster. The other thing we can do is we can calculate cost quantitatively, not qualitatively. Not, I think this is pretty cheap. I think this is better than the other design, but I have a number. So the benefits of optimizing are reduced engineering time, because you've reduced that design cycle by speeding up the vertical alignment and getting some hard feedback on your costs. And we hope that this then will lead to better designs. And of course, better designs will be cheaper to build. That's where the big savings are. If you can optimize your cuts and fills, which is what this is all about, you can have significant savings in the earthwork costs on an actual road. And we've seen examples of this. There's a couple of test cases we've run through, and human engineers in a long, complicated alignment with some significant terrain cannot match the software. Optimization it wins every time. Okay, let's take a look at the program. So I'm going to open up our road design package, and this is a full-featured road, single alignment road design package. And what we've done is we've built into it the Softree Optimal technology. And we're working on a bridge to go to Civil 3D. So this will become kind of a companion product that you would run with Civil 3D. But currently, it's, like I say, it's a road design program with the Softree Optimal built in. So let's just take a look at this design I've chosen for our example. It's a road realignment. You can see the old road in the background, and the new alignment is the heavy red in the foreground. The cross sections vary along the alignment. You can just kind of step through there and see, okay, there we are right on top of our culvert. Got steep fill angle here. I've actually applied a special material for this fill as well. And a little further along, you can see it gets wider on the left. We've got a turning lane in there for this driveway. And then as I go out further, you'll see that fill angle goes down. It's not so steep anymore. Probably should have put guardrails over the steep fill in this zone. I didn't bother because it doesn't affect the volumes. So it's a real design. It's got layers in the ground. We've got rock down here. It's kind of simple-minded layers. They're just a fixed depth, but you can put in surface layers of any shape or size. And there's a profile I've put in, and you can see that the mass haul has been calculated. I have a little bit of extra material which is being dumped in a pit at station 0 here, or trucked away, whichever way you want to look at it. Right, so I designed this by hand. Now let's take a look at what the optimization gives me. First of all, it gives me a cost. So you can see these numbers on the right-hand side. Total cost $473,000. I'm working in metric units here, but of course it works fine in feet and cubic yards. So that's why it says cubic meters here. And we got total hauls. There's a bunch of other information I can look at too. I got a data window here which has got curves in it. I've got another one which has volumes in it. So if I was just using this by, in the traditional way, I wouldn't have these total cost numbers, or maybe I would have some software that would calculate that for me. But here's the cool part. If I set up my recost to be automatic, which is reasonable for a relatively small road, this one's about 1 kilometer, or what, 0.6 or so of a mile, I can just change the alignment, and it calculates all the cross sections and changes the cost there. So that's now 500,000. Okay, that was probably a bad idea. Let's undo that. The other thing you can do is you can change the horizontal alignment, which is pretty amazing. So if I just change the horizontal, it recalculates all your costs. It figures out how to apply the profile to the slightly different horizontal alignment and comes up with a new cost. Well, that was a good move. I'm now down to $380,000. Okay, now I've changed the horizontal. I need to redesign the vertical, right? Well, not really, because that's where the optimizer comes in. So now I'm going to show you how it optimizes the vertical alignment. Any questions at this point?
So where do you have like all the design criteria for, design speed, the slope angles, super elevation?
Okay, that's done in our template. Well, there's a few places, but basically in this case we're designing a template here, and it's got some overrides for super elevation. You can see this particular cross section is super elevated, and the super elevation is calculated in the horizontal alignment curves. Here we're pulling them out of a table. A lot of this stuff is it's got to be in all design software that builds roads. It's pretty standard civil engineering, and we accommodate all that. In our link to Civil 3D, we're going to take the cross sections right out of the Civil 3D software with a little add-on, and so all of those parameters that define things like final slopes and super elevation and so on won't even be in this software. It'll just pull the cross sections directly. Right, so I've got a good horizontal here, and I'm going to now optimize the vertical. Before I do that, let's just take a look at, well, first of all, I'm going to create a new alignment so we can compare it with the old one. So we can have multiple verticals now. For those of you who are familiar with our software, RoadEng, you'll know this is new. This is out in version 7. Okay, I'm running out of imagination for names, so I'll just put optimal for the description as well. And I'm not going to calculate every cross section. I'll just do every 10 meters or 30-something feet. That'll speed things up a little bit. And standards. Okay, here's where we put in our curve standards. So when you're designing vertical curves, you may have a minimum curve length that you're looking for. You can also put in other types of curves here. But the one I'm going to use, back-to-back curves, is the fastest. And I'll show you the results of the other curves in a sec. I just don't want to do that real time because it can take quite a long time. One of the problems with a powerful but it's doing an extremely complicated problem. It takes a long time to solve the optimizer in general. We need some control points. This is a realignment. So at the start of the alignment, I want the road to match the elevation and the grade. This is easy because I've already got a vertical, so I'm just going to pull the grade off my hand design. I need one more at the end. So a control point. Control points obviously allow you to deal with things like intersections, bridge abutments, in this case realignment joining with the old road. You get the idea. Covering culverts, things like that. I have some pits defined here. This is the interesting part. How do we cost the road? I mean, you can't come up with a number like my total cost number here unless there's some raw unit costs for things. So here I've defined the cut and fill costs for each material. Solid rock costs more to cut. It has to be blasted. And in addition, we've generated costs for hauling, and it's using 3-stage hauling, probably bulldozer, scraper, truck and bucket, and we've got some unit costs there for hauling. All of these are configurable, save in a little file, use them over and over. The main point here is that it keeps track of cuts and fills, and it's pretty smart about using the right fill for the right zone. That's what the quality factor is for. Okay, so I'm ready to actually calculate this optimization. So here we go. Just going to do a quick feasibility test, make sure I haven't done something silly. This checks for geometric problems. Oh, I know one thing I forgot. When I was in the curve section here, I didn't specify my K-factor for vertical curves properly. And you can change also the minimum maximum grades. Let's say we're going to go to 8 and minus 8 for our maximum minimum grades. You can do different specifications for different station ranges, and that's true of a lot of the things in here, like constraints and so on. Okay, that's better. Now let's do the actual quick feasibility. Yes, it's going to work, and process. Now it's calculating not only the cross sections for the current alignment, but all the cross sections that might be used. You may have noticed a vertical offset parameter. This is looking up and down 10 meters on either side of the current vertical. And it's also, it's already finished. So this is where you don't want to get a little bit misled. This is already finished because A, I was using the fastest possible algorithm for calculating curves, and B, because it's only 1 kilometer long. Usually you can get away with waiting a few minutes, but it's not impossible to have a few hours. So yeah. So the blue line is the optimized alignment. Let's see what that looks like. So you can see it's put in a lot of curves. Not as many as you might expect because it combines curves with the same curvature, so they're not all 50 meters long. Some of them are longer. Notice that the volume is balanced. It's using my pit a little bit down here, my rock pit. There's a little tick mark in the mass hull, but mostly it's a balanced road. This is now 340,000, and let's compare it with the hand design that I had in there. So the hand design was 388. This is a 12% reduction in construction costs, at least the earthwork construction. And I did it at the push of a button. It's reproducible. So a point I want to make about reproducibility is that you can compare alignments now with this tool and say this alignment costs this much given these parameters for optimization. So in other words, you can put in 2 horizontal alignments, come up with an optimization set of parameters, and just look at the comparison of the two. When you've decided which horizontal alignment you want, then you can go back and do a longer optimization and get more reasonable curves. And I'll just open a design that has that in it already. Might want to look at this later, so I'll save it. So here's an alignment with a bunch of different trials, different vertical trials. By the way, I did this with a different horizontal, so the numbers are slightly different. But the final trial that I did is, notice that there are tangents between all the curves. I actually set it up this way so that it has minimum 100-meter curves, minimum tangent length of 50, and a flexibility of 25 meters. So there's basically 25-meter segments all along here, and it's fitting the curves as best it can using that limitation. And the result is a design cost here that's $417. If I go back on this horizontal alignment to trial 1, it's $404. And now I can see, look, I've got two horizontal alignments here. This one is $404. The one that I just did a second ago, I'll just open it up because I can do that, is there we go, 388. So, or 340, sorry. So obviously that horizontal alignment move was a really good idea. I should go back and use this horizontal alignment instead of the other one. Right, so I've covered what I wanted to show you in terms of optimization, and I wanted to ask for questions at this point. They're stunned into silence.
Your goal with Civil 3D is that we would define the templates in Civil 3D. You would read those templates. Is it still going to be a separate program, or are you going to run inside of Civil 3D as far as the optimization goes?
It's still going to be a separate program. Good question. What we're going to do is pull an array of calculated cross-sections out of Civil 3D using a little add-on that runs inside Civil 3D. And then then you would do the optimization here. Now, if you didn't have that add-on working, which is the current state of, you know, it's not finished yet, it's just in testing mode, you would have to design a cross-section in our template editor that looked similar to the one you were using in Civil 3D. So that's that's the bridge as it exists now. We can read in surfaces with Land XML, we can read in alignments with Land XML, but we can't read templates, so you'd have to redesign your template inside Roadeng. When the bridge is finished, it's going to pull those templates in for you, and it's going to just interpolate between them, and you won't have to do any template design inside Roadeng.
Okay.
Any other questions? With respect to Civil 3D, when you're finished, you can save your design as a Land XML. You can also save out surfaces. So any of the surfaces that are of interest, you can save. I think if you've already got the design in Civil 3D and you've already got your, what do they call them in Civil 3D? Assemblies all built, then you just need the center line. You just need the curves, and the vertical curves is really all you need, because the horizontals in general are not going to change. Yeah. So yeah, just to reiterate, what you've got here is a tool that will help you compare different horizontal alignments, because you can run multiple versions of location at the same time. It will generate the cheapest vertical alignment for any horizontal, and it does take care of all the various real-world problems that you run into when you're designing a road.
Well, thanks a lot, David. This was real interesting. Please send us the link to the recording, and we can circulate that to some of our CAD user groups and some other folks, and just to let them see the Softree software as well.
Okay. Well, thanks very much for your attention, and yeah, I'm glad that GoToWebinar thing worked well for you guys. Yeah, we'll be in touch. Cam, you have any final words?
Nope. Sorry, nope. I'm good.
Okay. Thanks again. Bye now.
All right, bye guys.
Bye.